Alright, so today we start arithmetic sequence, which is another application that we get with linear functions. So there's a few different vocabulary words I want to make sure that we discuss first. So first off, an arithmetic sequence is a sequence, or we talk about a pattern, sequence or a pattern of numbers, which increases or decreases by a constant amount. Now, a recursive pattern is a pattern which can be described by applying a rule to any term in the sequence to find the one after it. And then finally, the explicit equation describes the nth term of an arithmetic sequence in terms of the first term and the common difference. Okay, so hopefully as we go through these notes, this will become a little bit more clear, but these are the basic definitions for these three words that we're going to talk about. Alright, so first off, I'm going to go ahead and give you the explicit equation for an arithmetic sequence. Okay, so this is the explicit equation. A of n represents the nth term in the sequence. The first term in the sequence is represented by a sub 1, and d is the common difference between terms. Okay, so those are the kind of the information that we're going to have here. An arithmetic sequence is an example of a function that has a constant rate of change. So constant rate of change should automatically flag you to be a linear function, because that's one of the key characteristics of a linear function, is a constant rate of change. And so linear functions, of course, we know can be written in the form f of x is equal to mx plus b, where m is the slope of the line and b is the y value of the y-intercept. And so these two are related, and we'll see that in an example here in a little bit, where we take an arithmetic sequence and boil it down really into a linear function, because that's what it is. But one other piece of information we need to make sure we understand in this process is that any relationship which has a constant rate of change, constant being the key word there, is a linear relationship and is graphed as a straight line, like the example here below. This is a straight line, it is a linear relationship. A relationship which does not have a constant rate of change is called a non-linear relationship, and this would be an example of a non-linear relationship, but it's any relationship that's not a straight line. Okay, so these are kind of the basics. The best way that we can approach arithmetic sequence is by jumping into some guided examples. So we're going to walk through a couple of examples together, and then we'll kind of discuss this as we go. Okay, all right, so the first guiding example: Emmanuel is selling raffle tickets to raise money for charity. The table below shows the cumulative number of tickets he has sold each hour for the first 3 hours. So we're asked to state whether Emmanuel's ticket sales represent a linear or a non-linear function. Okay, so linear and non-linear, if you remember from your notes just a second ago, linear means it is a constant rate of change, creates a straight line, whereas the others are going to have a rate of change that is not constant. Okay, so that means that as he increases his hours, each hour, it should also be increasing the exact same number of ticket sales each time. So here from 14 to 18, we're adding 14. From 28 to 42, we're also adding 14. And so each time that we add 14, because it's constant, this makes this a linear relationship or linear function. Okay, now to determine whether the rule then it asks us to determine the rule which relates Emmanuel's ticket sales and time. So if you remember from our notes a second ago, there's something called a recursive pattern. And so the pattern is described by applying a rule to any term in the sequence to find the one after it. So here, what we're doing each time to find the next term is adding 14. So the rule here would be adding 14 tickets. Okay, that's what we're doing each time. In order to go from here to here, we added 14. To go from here to here, we added 14. So to find the next, it's going to be adding 14. To find the next, we're going to be adding 14. And so that becomes our recursive rule, or our recursive pattern. Okay, now if his ticket sales continue in this way, we're asked to determine the total number of tickets he will have sold after 6 hours. So we know that 1 is 14, 2 is 28, 3 is 42. So if we added 14, we'd be able to find 4, which in that case would be 56. And then if we add 14 more, we can find 5. So we would do 70 at that point. And then we can add 14 more, and that will give us, after 6 hours, how many he has sold. And so at that point, he would have sold 84 tickets. Okay, so just adding that recursive rule each time, adding that amount, is what makes that linear. It's what has the constant rate of change, and all of that. So that's kind of how that recursive pattern and the linear versus nonlinear kind of all goes together. So let's talk through this explicit equation idea. Okay, so here we have tiles that are stacked in a pattern. We have stack 1, stack 2, stack 3, and stack 4, and we'll notice how many that this table, it represents the relationship between the height of the stack, so how many tall it is, versus the number of tiles, versus the number of tiles in each stack. Okay, so we've started but not completely finished this table. We know that in the first stack there was it's 1 high and there's 1 tile in it. This one is 2 high and there are 3 tiles in it. Here we notice that we have 1, 2, 3 high, and there are 1, 2, 3, 4, 5 in it. For 4, it is 1, 2, 3, 4 high, and it is 1, 2, 3, 4, 5, 6, 7 tiles in the stack. Okay, so we're asked to describe the recursive pattern. So this is kind of the information that we have so far. So we'll notice that every time we add a height layer to it, we are adding 2. So that lets me know that this is a linear function. I'm going to be adding the exact same amount each time, and so we're asked here to describe the recursive pattern. So the recursive pattern is that I'm adding 2 tiles each time we add another height, okay, or another stack to the height. Now, the explicit equation is where this equation is going to come into play. This a of n is equal to a sub 1 plus d multiplied by n minus 1. That's where this is going to come into play. So we can take this information that we have and plug it into this equation that will work, so that instead of just having to add 2 every time to find the 5th and the 10th and the 100th, we can actually plug that 5, 10, and 100 into an equation instead of having to count out what it would be at 100 high. And so that's what we're going to do here, is create this equation. So a sub n is going to represent the nth term of the sequence. This right here represents the first term, and here we have 1. In the first height, there is 1 tile. So 1 is going to be my a sub 1. The difference here is how much I'm adding each time to get there. So I'm going to add 2 each time, and then n represents that height of the stack each time. Okay, so here is my explicit equation. We write it as a of n is equal to 1 plus 2 multiplied by the difference of n and 1. Okay, and it doesn't seem to make a lot of sense right now, but we'll kind of talk through this a little bit more in class and as we go through additional notes with arithmetic sequence. Okay, so this is going to be where a sub n is the number of tiles total, and n is the height of the stack.